Okay, this video is specifically on conditional probability and independence, but we are going to look at independence in a variety of lights. So first off, this says, this is not on your formula chart, by the way, so you're going to have to memorize this. If the probability of A given B, remember the line means given, A given B equals the probability of A, then events are independent. So once again, if the probability of A given B equals the probability of A, then the events are independent. Of course, I could have changed this around and said the probability of B given A equals the probability of B. If that's true, if that is true, it's not guaranteed to be true, but if that were true, then the events are independent. Now remember, what we have already previously said is the probability of A given B equals the probability of A and B over the probability of B. So the probability of A and B, that's just saying that's that. That's just a property. If that's the case, if it's independent, if it equals the probability of A, then independent. Well, what's interesting about that is that sort of makes sense, because what was our multiplication rule? Our multiplication rule for independence said the probability of A times the probability of B equals the probability of A and B. And that was true if they're independent. Well, if I divide both sides, by the probability of B, this goes away, and I find out that the probability of A equals the probability of A and B, that should be an A, over the probability of B. So basically just from algebra, it's an algebraic manipulation, but sometimes College Board wants you to use that formula. And since this happens to equal this is always the case. This part right here is always true. So because this is always true, but if this equals this, then this must also equal this. But it's only the case if they're independent. This part that's circled, always true. This part out here, only if independent, okay? So we previously talked about independence and proportionality. When we did this with the right-handed and the left-handed scenario, and we said that they were all proportional because 190 over 1900 is 10%, 10 over 100 is 10%, 200 over 2000 is 10%. Because they had the same proportions, we said that we said, hey, you know what, these are independents. So let's demonstrate this using the multiplication rule, and it says we're going to start off using percentages. Now I could have chosen any group. Turns out I'm going to choose left-handed and normal IQ. So if I do that, I should be able to go the probability of A times the probability of B equals the probability of A and B. So 0.05 times 0.90 should equal 0.045. And if I multiply that out, I find out, yep, that's true. And because that's true, the events are independent. And we need to sit there and you need to actually make the comment. You write the formula, you plug in, and the events are independent. All right, therefore the events are independent. You need to make a statement to that effect. If I had used actual values, I would need to set up something, and I could have done 90 over 100 times 1800 over 2000. I chose not to do that because that would have given me exactly the same answer. So I decided to use this part over here. All right, so what's the probability? And so I decided to use normal IQ. And the probability of A and B equals the probability of A times B. So I'm using 1900 over 2000 times 1800 over 2000 has to equal 1710 over 2000. It does. Therefore, the events are independent. All right, so we could have used actual values, but to use actual values, technically all I'm doing is dividing to make them into probabilities. I could have gone 0.95 times 0.90. If I'd done that, I would get 0.855. 0.95 times 0.9 equals 0.855. And the reason is all we did here to create this table here is take every single one of these values and divide by 2,000. So by dividing by 2,000, I create this table. So consequently, they're essentially the same table. But if you're using by actual values, all you're doing is dividing by the total. The next thing says, demonstrate using conditional probability. So we want to do the same thing using conditional probability. And remember, with conditional probability, we're going to say the probability of A and B equals the probability of A. This is only true if independent. And also we can actually add one other piece to this. It's not going to help us for this problem, but you do need to know this, equals the probability of A given B. All right, this is the probability of A given B. So this is the intersection divided by B needs to equal A. So when I look back at this, so I go back and look at my table, and we want the intersection divided by B, and we're defining B as the 90%. Okay, so this is, I'm saying this part right here is B, and I'm saying the 0.05 right here is A. So this is my intersection. So if my intersection divided by B equals A, then independent. Well, sure enough, my intersection divided by divided by B equals A. So intersection divided by B equals A. Because that's true, they're independent. Okay? I could do the same thing using actual values. The only thing with actual values is all we're doing is dividing by 2,000. A little bit uglier, but it still does the same thing. So please remember, if independent, A intersect B over B equals A. And that equals the probability of A given B. Okay? There are times that you're going to be required to use this method. Most of the time, the multiplication rule works really well. Sometimes proportionality is going to be useful. But so you're going to need to know these three methods: proportionality, the multiplication rule, and then conditional probability. This one was a big one in college. They tended to allow us to use this, but they expected us to know this, and sometimes College Board will expect us to know this. And I will show that in the next video. Okay, thank you.